bar for reactant, H bar F plus H bar minus H bar naught for reactant must be equal to Q dot out plus work dot out plus sum of N, this for product, N dot product, H F per mole base plus H for product. If we divide it by molar rate of flow, that means how many moles of fluid passing through, because this is the same flow coming in. This is per mole. That's a mole. If you want to divide it by number of mole of the fluid coming through per unit what? Time. Whichever you pick as your molar ratio. So this, I'm not going to rewrite it. Well, let me, for 1 mole of fuel, if you want to have it per mole ratio, you have to divide it by number of moles per unit time. For 1 mole of fuel, you can write it like this. Per unit time. All we have to do, put down Q dot over N. Well, let's say for, not for N, but for N mole of fuel per unit time. So we divide it by number of mole of fuel coming through, plus W dot N equal to plus what? The rest of it was summation. You can write it like that. That can be written as, we can reduce it. So for this, if this is number of mole of fuel, everything going to be per 1 mole of what? I'm just writing it, dividing everything by what? N dot. I don't have to do that. Just put parentheses around here. And put 1 over what? N dot. Are you with me? So this is going to give me this. I get Q minus W equal to output on. Let me write a little bit. The way it is would be Q dot N, Q dot over N dot minus plus N minus Q dot over N out. I'll try to avoid that, which we can write it as a Q minus W. That is Q. And then we can do the same thing. See, we can bring them out and here, combine them together. That will be your that Q. And then we can put down W dot over N minus W dot over N dot out. We call this W without any dot. And then if we make this this change of this formation to simplify the formula, we're going to have Q minus W equal to summation of NP H minus N reactant. You bring a reactant from the left side to the right. This essentially simplifies it. Just put this here, put it for, this will be for 1 mole of fuel. And these are going to be ratio of, like if you have 1 mole of fuel, how many mole of oxygen, how many mole of nitrogen, this is going to be the numbers. Because formula we're writing, the reason we're writing that because of chemical formula, we always use 1 mole of what fuel. So that means you can look in the formula and you can see directly these factors. That's the reason for it. And for a closed system, this is for an open system. We don't have to do much. Just replace H bar minus H bar naught. We have in here. Replace it by U bar minus U bar naught. To get, then this is going to give us we have to do something like this. To get U bar not equal to H bar minus H bar naught minus PV. I don't have to put it here. That's all I think. And these are material Yeah, look at the equation number 1510. This is this one. And for a closed system, equation 1550. And let me go over those a little more with detail, and then we yeah. 35. Finally, in summary, we're going to have a you have Q in minus W in. Remember, that's per unit 1 mole of fuel plus some NR or reactant must be equal to Q out plus W out. The only difference is we took a dot out and we put number of moles of a reactant per unit per mole of fuel. And we had a Q minus W equal to some, put them in the same side, and P H which is this is a H of a product, and this is a H of a reactant. So we're really saying Q minus W equal to H of product minus what? H of reactant. We can write same thing for a closed system. This is we repeat that, minor changes, becomes Q minus W equal to NP H bar not F plus H bar minus H naught minus PV minus an R this is for product and that's for reactant. Well, if you have there is very often we try to get adiabatic condition in order to get flame temperature. That means if you're burning, say octane with oxygen, and you want to know, and the closed system, you want to know how hot the gas gets. In this case, both Q and W are what? 0. So, for pure combustion, adiabatic temperature for pure combustion obtainable when Q is equal to 0 and W equal to 0. Then that means then we got H of a product must be equal to H of a reactant. I think this is what book uses in example 15.8. You see that? (15.8) uses a. I'm not going to go through it, just highlight it. It uses C8.4, C8, H18, octane, pure combustion, O2 plus 3.76 N2. Going to give us 8 CO2 plus 9 H2O plus 47 N2. And then for liquid, C8, H18, we got H, F equal to minus 24995 kilojoules per kilogram. For H2O, we get 241,820 kilojoule. That's kilojoule per kilomole. That's kilojoule per kilomole. And then for CO2, it's minus 393,520 kilojoule per kilomole. Yeah. You put all these in equation, in this equation, which I'm erasing. We get 8 times minus 393,520 minus 8 plus H bar of CO2 minus 9 at 25 degrees. CO2 has 9364, and then plus for water we have 9 moles multiplied by minus 24,1820 plus H bar H2O. We don't know that. We have to leave it blank because we don't know what temperature is, final temperature. H2O minus 8, and we know at 25 degrees C, which is 8669, this would be equal to 1 mole times minus 294,950. A 50 missing here. And this is going to give us, combine all numbers together, we get a 9 H bar CO2 plus 9 H bar H2O plus 47 H bar N2 equal to 5646081 kilojoules. Now, we want to calculate temperature.
Wouldn't it be 8 for CO2?
Let's see, 8 CO2. Looking around for the paper. Now, we go to table for, not the reaction, just a regular table for gases. For CO2, you can have enthalpy as a function of what? Temperature. You have water as a function of what? Temperature, water vapor. And you have nitrogen as a function of a temperature. And you pick up a temperature, you guess a temperature. You pick those from a table, multiply, and see if you get this. If you're not, if you get the lower value, then raise your temperature. So you have to play a game when you're going to have what? Right value. So you end up, the final result is T approximately is equal to 2395 K. And in the book, it repeats the process for 400% theoretical air, right? And it gets temperature of 962. If you have excess air, 300% excess air, which is 400% theoretical air, that means instead of using 12.5 here, you're going to use what, 50, right? He uses 50, doesn't he, in the book? Example 8. Yeah. Yeah, he uses he repeats the process for a I get 962. See the equation in the middle of that. So it really depends on a case, and you can calculate how hot the gas gets after it is what? And any questions? Actually, it's 10 till now, right? Perfect time to quit. If you don't have any questions.